But okay, so from yesterday, I promised that I'll also give you this radius for the innermost stable circular orbit for the Kerr metric. So the Kerr metric was discovered in 1963. What it describes really is an isolated rotating black hole, and it has only two parameters. It has the rotation parameter A, and it has the mass m. And so the rotation parameter A is related to the angular momentum of the black hole J by simply J over m. So A times m is J. All right. So now, of course, we are making a tiny perturbation, treating the accretion disk as basically test particles on the background of the Kerr geometry. They don't backreact on the geometry, so the geometry is still sort of Kerr. And so based on that assumption, you can calculate how close you can actually go to the black hole, how close is the last circular orbit. And so below this, so you can have the accretion disk all the way to that radius, but once you actually get closer than that, you just simply fall to the black hole, and there is no, so it will not radiate anymore. Okay, so this is the formula. That's supposed to be B. So you see that it's quite complicated, and it's moreover, it's only valid for the motion in the equatorial plane. So now the Kerr metric actually depends non-trivially on your theta direction, and the motion. So the motion is in general very, very complicated around Kerr black hole. It's still integrable because of this hidden symmetry of the Killing tensor and Killing-Yano tensor, but nevertheless, it's quite complicated. And so that's why also the formula is quite complicated. So there's this variable x, and x is simply A over m. So now if A is 0, we are back to Schwarzschild. So if x is 0, we should be recovering 6m. And so that's what we derived in the previous lecture. On the other hand, you can go all the way to x equal to 1, in which case A equals to m, and such a black hole is called extremal black hole. And if you keep increasing A even further, suddenly the black hole horizon disappears, and you have so-called naked singularity. So the black hole basically disappears, but you still have something which is singular, at the center, but it's not cloaked by the horizon. And people believe that such things cannot arise in physical situations. So if you have gravitational collapse of something, people believe that it will never give rise to the naked singularity, and that always the final stage will be a black hole. So now this is a big question already from 60s. And people like Penrose were trying. This is called cosmic censorship, and it basically says if you have smooth initial data, then you can never produce a naked singularity out of these smooth initial data. So now this has been recently very much questioned, and there are certainly violations of this in ADS space or in higher dimensions. But I think in a vacuum and in 4 dimensions and in asymptotically flat case, which we are interested in, this still actually sort of holds. All right. So are there any questions to this? So by the way, so there is this plus minus, and it corresponds to whether your matter is actually co-rotating with the black hole or whether it's counter-rotating with the black hole. And then you see that they really split. So whereas the one, I think, is the prograde one which goes down. I'm not sure whether I didn't switch these two, but let's hope. And this one goes all the way to 9m. Okay, so when you asked me yesterday, is it bigger or smaller? It depends on whether you are co-rotating with the black hole or whether you are counter-rotating against the black hole. All right, but anyway, so people hope that they will measure this thing here, that they have so good resolution by this Event Horizon Telescope that they can actually see this, and they can compare this R ISCO, whether it's precisely as predicted by general relativity or whether there is some deviations. And that would, of course, mean that maybe we have to modify general relativity. But it's not so simple to modify general relativity. People have been trying, and there is no consistent theories, basically. All right, so the last thing which I would like to discuss today is black hole thermodynamics. And this is like a funny topic at the end. And as I said, it won't be in the interviews. And so let us start with the motivation. And let us start with the Schwarzschild black hole, which we already know very well. So our metric is ds square is minus f dt square, dr square over f plus r square d omega square. And f is 1 minus 2m over r. All right, so now let's study some properties of this metric. So we already studied the maximal extension. I was trying to convince you that if you approach the horizon, which is located at r equal to 2m, then things get frozen there. You have a surface of infinite redshift and so on. But let's, for example, calculate what is the asymptotic mass of this thing here. So as I said, so if you want to calculate energy in general relativity, it's typically very, very complicated because the energy is not localized. But it makes perfect sense to talk about the energy of asymptotically flat spacetimes. And of course, you intuitively understand that energy should be somehow connected with some time translation invariance. Okay, and so this metric is actually a very good one because it doesn't depend on time at all. Okay, so the metric is static. Metric is static, and so for this reason, defining energy should be easy. So there's a dt equal to k killing vector, and for this reason, defining energy should be really, really easy. It should precisely correspond to this translational symmetry in time. And indeed, this is so. So you can define so-called Komar mass, and that can be defined for any stationary spacetime. So as long as you have a killing vector, which is asymptotically time-like, then you can define this Komar mass. And it's simply given by, I'll write it in fancy notation, minus 1 over 8 pi, integral over sphere at infinity, and then I'll write it in differential form notation, star dk. Okay, so k is a vector. I have to make it a form. Then I take its derivative, exterior derivative, and then I take its Hodge dual. Okay, so of course you can write it in components, but it will be using the epsilon, and then it will be antisymmetric derivative. So you would have to write something like epsilon mu nu rho sigma, and then d rho k sigma. And so this is the quantity which you are basically calculating. But what is important is really that I'm using this time-like killing vector, which tells me about the time translations. And actually, I'm calculating this integral at infinity. So where, my spacetime is asymptotically flat. So okay, so if you do this, you just find a big surprise. What do you think this is equal to? M. Right? So we are calculating the Komar mass, and this better be whatever we call the Newtonian mass for objects like this. So m is equal to m. That's fine. So this is really like the total mass or energy of spacetime. In our case, it's just the mass of the black hole. All right, so we have one quantity which is quite interesting, and that's the total energy in the spacetime. So then another quantity which may be a little bit counterintuitive is the surface gravity. Which is, if you want, an analog of gravitational acceleration, of Newtonian gravitational acceleration on the black hole horizon. On the horizon. So we want to basically know how strong the gravity is if you evaluate this on basically on the black hole horizon on r equal to 2m. So, okay, and so there's a strange formula for this, and the statement is that the black hole horizon, which we know is located at r equal to 2m, is so-called killing horizon. Is killing horizon. Again, it's not killing anybody. It's still the same guy killing horizon. And what it means is that basically, any hypersurface. So the black hole horizon is some kind of hypersurface, and as such, it will have a normal to it. Okay. So now, so you can characterize hypersurfaces by this normal. So now, killing horizon is such horizon which actually has the normal given by a killing vector. But moreover, this killing vector is actually null. That means that the norm of the killing vector is 0 on that hypersurface. So killing horizon, that means it's generated by killing vector, which is normal to that, but which is also null, which is null. That means k squared, okay? And so it's precisely this killing vector here which generates your horizon. So the statement is precisely this dt killing vector satisfies on the horizon k squared when r equals to 2m will be 0, but also the surface r equal to 2m is actually the normal to this surface is given by k. So k mu is the normal to r equal to 2m surface. Okay, so that's what it means. Okay, so that's that's not important, but it's a nice property to have. And then the statement is, once you know that your horizon is actually a killing surface or killing horizon, then you can easily calculate the surface gravity. And then I'll give you the definition and you will tell me what it means. So the definition is, I take this killing vector which generates my horizon and calculate the following quantity, nabla mu k nu, and then this will be equal to k nu. Okay, have you seen this equation before, and what does this equation mean? It's a geodesic equation. Exactly. So what actually we are telling, or I'm telling you here, is that if you have a killing horizon, then this killing vector, which is generating my horizon, is actually geodesic. It's a null geodesic because k squared equals to 0. So k is a null geodesic tangent vector. But also it's telling you that, well, typically you would have 0 on the right-hand side, right? You would just have k mu nabla mu k nu equals to 0. And we know that we only get non-zero provided that we have stupid parameter parametrizing my geodesic. So this thing here arises from the fact that we don't have affine parametrization of my geodesic. And so this kappa, which is basically, so this is a definition of kappa here, and it measures how much the parameter is not an affine parameter, affine parameter for my geodesic. So the statement is, k mu will always be null geodesic on the horizon, but it's not affine parametrized, and this non-affine parametrizations define this kappa here. So if it's not affine parametrized, you will have non-trivial kappa, and that's a definition of this kappa. And so kappa is called surface gravity. So kappa is called surface gravity. All right, so now you can calculate what it is. So just from this definition, you just have to calculate, k nu is just dt. So it will have components 1, 0, 0, 0. And you can calculate whatever the left-hand side is, and then you can read off whatever the kappa is on the right-hand side. And for the metric, which is of the form minus f dt squared dr squared over f, the statement is that this kappa simply is given by f prime divided on the evaluated on the horizon divided by 2. So df over dr, and now we evaluate that at r equal to r plus. And so this is given by 1 over 4m or 1 over 2r plus. Okay, and so this is what you find for the surface gravity of our Schwarzschild black hole. Okay, so that's easy peasy. So the statement is, on the horizon, the gravity is strong like 1 over 4m. Okay, so you see that bigger the black hole I have, the strength of gravity is smaller. So on a horizon of really, really large black hole, basically kappa is, it's negligible. So by the way, I said this is like an analog of gravitational acceleration for the black hole. Okay, so let's calculate the gravitational acceleration. So G for Newton. Well, it's m over r plus square, right? So if I have an object of mass m, and I'm interested in the distance r plus from the center, so this is the gravitational Newtonian acceleration, well, this is m, and then 2m squared, which is 1 over 4m. So actually, this exactly coincides with the Newtonian prediction. Of course, this is just a coincidence, right? So, but you can really think about kappa like the gravitational acceleration on r equal to r plus. Okay, this is just a coincidence. But it's a cute one, right? So you can just do with the Newtonian theory, and then you know what the surface gravity is. All right, so we have two concepts. We have the mass, or total energy of the space-time, and we have the surface gravity. So the last concept is very, very simple. Let's just calculate the area of the black hole. So finally, we want the horizon area. Okay, so this is our metric. And so on the horizon, you can calculate with our loss of generality at t equal to constant. So we are taking our metric here and calculating how big the black hole is. This doesn't depend on time, so let's calculate it at t equal to 1 or t equal to 0, doesn't matter. And then we know that r equals to r plus on the horizon. So r equals to r plus. So what it means is that the first two terms in my metric disappear. So t is a constant, so dt is 0, and r is r plus. So the second one is also 0. So now I have induced metric. So induced metric on the horizon is simply I just plug these two into my full metric. So it's d gamma square, or d gamma square is simply r square d omega square, and r I evaluated r plus. So it's r plus square d omega square. And so what is the corresponding determinant of this metric? Huh? It's just the metric on the. So this is d omega square, right? So d omega square is d theta square plus sine square theta d phi square. So it's just whatever the spherical thing is. So now I'm taking the square root, so it's r plus square sine theta, right? So now if you want to calculate how big the surface is, the statement is get the area, just take an integral, square root of gamma, and you calculate it over d theta d phi. That's the volume element we have seen all the time, right? So now I'm just taking two-dimensional metric, but anyway, so that's the volume element. And so this is simply equal to r plus square integral sine theta d theta d phi, which is 4 pi r square. So let's call this capital A, and that's our area, how big the surface is of our horizon. So now we have three quantities. We have total energy, we have the surface gravity, and we have the area of the horizon. So now let's just play with them. So now, observation. Let's call it an experiment, theoretical experiment. So you may have a stupid idea to just differentiate what happens with the mass. Okay, so you can just calculate what dm is. Of course, the mass is just, well, r plus is 2m. So m is r plus over 2. So this is dr plus over 2. Very good. That was simple. And then we can calculate also what dA is. And so I have to differentiate this thing, and it's 8 pi r plus dr plus. Okay, so far so good. And then you may calculate what is kappa times dA, or better, what is kappa over 2 pi dA over 4. So let's do it. So kappa we derived, it's over here. It's 1 over 2r plus. It's 1 over 2r plus divided by 1 over 2 pi. And then dA is this thing here, 8 pi r plus dr plus divided by 4. All right, so we have something strange here, 2r plus. All right, and so if you see that, then this becomes dr plus over 2, which is precisely dm. So what you just derived is so-called first law of black hole mechanics. And so we have first law of black hole mechanics. And that's telling you that dm equals to kappa over 2 pi dA over 4. Okay, that's valid for Schwarzschild, but you can do it more generally, as we will see in a minute. All right, so we just have this observation here. Everybody happy so far? Observation is simple. Okay, so somehow the total energy in the space-time is related to the area change of the black hole times the corresponding surface gravity. Okay. So that's the motivation. So now, if there are no questions, let me proceed to more general laws of black hole mechanics. And so this is 1973. And gentlemen like Bardeen, Carter, and Hawking. Bardeen was here just a couple of weeks ago, so maybe you met him. Okay, and so they formulated the corresponding laws, and so they are not only valid for Schwarzschild black hole, but more generally, your black hole can actually also rotate, and theoretical black holes also have charge. So, okay, so general black hole has the mass, has the angular momentum, but can also have a charge. It can have other things. It can have magnetic charge as well. All right, and so then they formulated the following law. So the zero law says that the surface gravity kappa on the horizon of any black hole will always be constant. So if you look at the definition, of course, if I just define it as a measure how much my Killing vector is not affine parametrized, this is in general a function. So kappa is a function. Now what I'm saying is that this is not a function, but it's actually a number. It's given by some parameter of the black hole. Okay, so now, this is the first, the zeroth law. Then you have the first law, and that says that dm is kappa over 2 pi dA over 4 plus omega dj plus phi dq. So we already know this term. So now we are varying the angular momentum of the black hole, and this is the corresponding angular velocity of the horizon. So this is the angular velocity. So basically, how fast is your black hole rotating on the horizon? And so dq is the change of the charge of the black hole, and this is the electrostatic potential. So static potential again on the horizon, or so what this really is how much. So your infinity can also rotate, and your horizon can also rotate. So now the difference between the two is what you would call omega. So similarly, you can have some non-trivial electrostatic potential at infinity and on the horizon, and so then the difference of the two is this phi here. Okay. So, but it's this is the standard conjugate quantities in thermodynamics. Your phi and q are conjugate quantities, and omega and j are conjugate quantities in thermodynamics. So in other words, you are getting this nice term here, which is kappa dA over 4 plus some work terms. And either the work term is due to rotation, or the work term is due to the charge of the black hole. All right, so that's the first law. And they also formulated the second law, which was basically due to Hawking. And so that said that classically, and provided the null energy condition is satisfied, you now know what it is. The horizon, the area of horizon never decreases. That means dA is always bigger or equal than 0. So the black hole can only get bigger, but it can never get smaller. And finally, there is a third law, which is still a discussion. But nevertheless, basically you can say it's impossible. It is impossible to reduce kappa to 0 in finite number of steps. So now, isn't this amazing, right? So you have these 4 laws, and they just copy whatever you know from thermodynamics, right? So if you say that kappa is somehow related to the temperature, and so this raises the question: is kappa related to temperature, and is the area related to the entropy. And if that is true, then what you see here is nothing else than the laws of thermodynamics, right? So the third law is telling you I cannot achieve t equal to 0, the absolute 0, in a finite number of steps. This one tells you the entropy has to always increase in an isolated system. First law is just, then the first term, if kappa is temperature, so the first term is something like T times ds. And then we have the work terms as we know them. And the first and the zeros one tells you, well, T is constant for an object, and that's also true in equilibrium, right? So this will suggest that this really copies the laws of thermodynamics. By the way, this is not in anyhow how they were derived. So they were purely derived on geometrical considerations, basically assuming that the horizon is the killing horizon of some killing vector, and then doing geometry on this, you can just derive these laws. So there is no thermodynamics input whatsoever. It's all geometry. So the proof of this is all geometry. And so it's really, striking how can Einstein equations know about thermodynamics? Okay, but of course, at the same time, these gentlemen wrote, well, this is just a striking resemblance, but it has nothing to do with thermodynamics, because we know that the temperature of the black hole is 0. Okay, so how can this be? How can this be? So if the black hole had non-trivial temperature, it would have to radiate, right? But we know that classically, the black hole only absorbs things. It can only, it's an ultimate sponge. It eats everything, but it doesn't give back anything. So how can this be? The classical temperature of black hole is absolute 0. It is an ultimate sponge rather than it's a sponge. Just absorbs everything, but never gives anything back. All right, so that was the status of. So they said, well, this is a striking resemblance, but of course, there's nothing about it because the temperature of black hole has to be equal to 0. So I cannot really make this identification kappa with temperature and area with entropy. All right, and so then Wheeler came with this great idea, which he gave to Bekenstein, his student, and he said, okay, so, but if really the black hole temperature is 0 and doesn't make sense to talk about the entropy of the black hole, then what happens if I take a cup of tea and throw it into the black hole? Okay, so this cup of tea carries some entropy with it, right? And so if I throw it into the black hole eats it, then where did the entropy go? What happened to the entropy? Did it completely disappear? Or actually, maybe this entropy is somehow stored inside the black hole. Okay, so that was the Wheeler's cup of tea. Wheeler's cup of tea. And so based on this task, so Wheeler always gave these really nice problems to people around him, but he never calculated anything himself. Yeah, one of the reasons is that he didn't really have the technical skills. But no, it's not true entirely. No. Yeah, so he had like lots of ideas. So anyway, so he gave it to Bekenstein. So he asked Bekenstein to actually look at this. And so Bekenstein came with a thought experiment, with this granting experiment with the cup of tea, and he somehow concluded that really the change, that the entropy of the black hole has to be proportional to the area. Okay, based on this, analyzing this cup of tea, he came up with this answer. Okay, he didn't know what the proportionality constant is, but he concluded that necessarily the entropy, so the black hole carries entropy. Black hole carries entropy. Entropy. And this entropy is proportional to its area. Okay.
How did he compute this?
Okay, just look it up. Yeah. No, so he performed some thought experiment, and yeah, based on this argument, just say, well, if I throw in the cup of tea, the only thing which actually changes, is that the black hole gets slightly bigger. So now, this somehow has to correspond to the increase of entropy, which carrying the entropy of the cup of tea and so on. So that was like an experiment. So he proposed this. But of course, this actually doesn't make any sense, right? So if you say this, entropy is area, then you have to conclude, well, that kappa is something like temperature, or you can conclude that kappa is something like temperature. But there is no verification why this is still true, right? So there is no radiation outside of the black hole. But this is only true classically, and so then Hawking in 1974 actually showed that if quantum effects taken into account the black hole actually radiates. Black hole radiates. And so in his approximation, the radiation is the simplest possible one. It radiates as black body, with temperature is temperature when, now I will restore the units, but it's basically k kappa over 2 pi. And then the units are h bar kb and okay, so this is the temperature with which the black hole radiates. So really the temperature is proportional to the surface gravity, and so then you can identify kappa over 2 pi with the temperature, and then just looking at our laws, that means that the entropy, so now this really makes sense, and it's a thermodynamic expression, then the entropy has to be area over 4. And then from here, it follows that S is A over 4, and then you can write down the units as well. So the units are h bar and then g. So basically, he fixed the proportionality factor, which Bekenstein couldn't get. He just got it, get it by some argument, but he fixed it by calculation to be 1 over 4. Okay, and so that's what Hawking showed. So by the way, so this was a derivation using QFT and curved space-time. You may actually do the actual calculation in your cosmology review course if time permits. Probably not. But yeah, it's some calculation to do. But basically, what he is doing is that he studied the stimulated emission. So he shoot at the black hole some scalar field. Okay, so this is my horizon. So remember, in the Pascal diagram, I had the horizon here, r equal to 2m, and I would have the singularity here. But anyway, so what he did is that he shot some scalar field, and this scalar field sort of raised the surface of the black hole, and scattered around by the black hole, and some scalar field can go inside, but some actually goes close to the horizon and goes all the way to infinity. Okay, so this is what he did, and so he shot some flux of the scalar field here, and then he calculated what is the flux of the scalar field at infinity after it scatters by the black hole, and he actually realized that the flux is bigger than the original one which you started with. Okay, so then actually there was like stimulated emission, if you want, stimulated emission of the scalar field, and then he showed that this follows the Boltzmann law, and the corresponding temperature. Okay, so this was the original derivation using QFT in curved space. So this is in QFT in curved space. And although people were really excited, there were lots of people who hated it at the very first moment. And the reason is very, very simple. So if you use QFT in curved space, what it means is that basically you fix the geometry to be classically and fixed, and you just consider quantum fields on this fixed space-time. All right. So he's basically treating the scalar field as a small perturbation, which doesn't do anything with the geometry, right? But you remember that if I shoot something from infinity with a finite energy and finite frequency, as I go closer and closer to the horizon, the frequency increases because, right? So it's a surface of infinite redshift, or if I go the other way around, it's a surface of infinite blue shift. So everything here gets infinitely blue shifted. So actually, if you calculate what are the frequencies of the scalar field around the horizon, which Hawking needs to actually calculate this amplification, they are like of the order of 10 to the 68 or something like that of the original frequency. Of course, energies like that will necessarily break the test field approximation. They will modify the geometry around the black hole, and that's why people never believe that this derivation is actually correct. And so people like Bill Unruh, he still doesn't believe that the derivation is correct. And so that's why he designed his own derivation, which doesn't need this. Okay. But anyway, so although this completely, the first calculation is probably completely wrong because you just neglect all these very important effects. There have been many other derivations of the same result, and people agree on using various completely different methods, using string theory, using loop quantum gravity, using Euclidean path integral, or other methods. So people agree on the same result, right? So although the original derivation is probably completely wrong, it gives the right answer. Are there any questions? All right, so now we have actually promoted those laws of black hole mechanics to really laws of black hole thermodynamics. So now this is the origin of black hole thermodynamics, where they say, well, actually now, if I take quantum effects into account, the black hole does radiate in mix, and these laws are nothing but the laws of thermodynamics taken for black hole as well.
They had to update the second law, right?
The second law, yeah. So it will be only the total entropy, which is outside of the black hole, plus entropy of the black hole, which has to increase, or something like that. Yes. All right. So now, as I said, you may see this derivation in your cosmology review course, where you will study a little bit of QFT in curved background, but probably not. So I will show you a shortcut. And so the fastest way how to obtain these results is actually through this Euclidean path integral method. And you will see that it's like, to derive these results, it's like maybe half a page. Okay, so I will just derive this for you. But this is using the Euclidean path integral for gravity. And so there was a huge debate so this was, again, developed by Gibbons and Hawking and people in Cambridge. And then there was a huge debate that actually this doesn't make sense whatsoever. And so there was even a debate between Roger Penrose and Hawking, which sort of reminded the debate between Bohr and Einstein about the fate of quantum mechanics, where Einstein was very conservative and was saying that quantum mechanics is incomplete, and Bohr was saying, well, this is actually what we have. So similarly, Roger Penrose was saying, well, all this Euclidean thing, it doesn't make any sense. And Hawking was saying, yeah, I developed it, so it makes sense. So anyway, I'll just present this Hawking's argument here. So let's just derive this. Derive this using Euclidean trick. All right, and for this, I need two things which you will get to know a little bit later. So one thing is that the thermal green function, you will derive this in your QFT2 course. Thermal green function has periodicity in imaginary time and so, okay. So this is your original time, and so the prescription is that now you bicrotate your time and form this quantity tau. And then the observation is that if you take a green function for a thermal system, this will obey, it will have the periodicity in this imaginary time tau, and this periodicity beta is precisely related to the temperature of the system. Okay, so this is the statement. So any thermal function will have this periodicity. And this periodicity in the imaginary time is precisely related to 1 over the temperature of the system. As I said, you will derive it in QFT2, but people take this as a definition of what thermal thing actually means. So whenever you calculate some, green function, and if it has this periodicity, you say it corresponds to a thermal green function, corresponds to thermal state. It's a definition of thermal state. So if I observe, I switch just t to I tau, it, t to tau, which is it, and observe this periodicity, then you say my state is thermal, and there's the corresponding temperature. All right, so that's first statement which you will need. And then second statement, which probably is more familiar, is that you can calculate a partition function in statistical physics. Partition function. Okay, so Z, and you can calculate it, again, you will derive this in QFT2 course, but you will calculate it as an integral, so let's push it. So this is certainly true for normal fields, but let's push it for gravity. So then it'll say it's a path integral over all metrics, and then of the weight which you put here is just the classical action for gravity in the Euclidean sector, meaning I just did this bicrotation time. Okay, so this is how you would calculate this. And then in the WKB approximation is simply given by the leading order by the classical solution. So this is for any metric, any fluctuating metrics around whatever. And then here I'm just choosing those which are classical metrics, which contribute most to my action. Okay, so I'm taking the stationary limit, the WKB approximation. All right, so this is how you would calculate your partition function. And then once you know the partition function, you can use the machinery of statistical physics. And so in particular, you can calculate what the free energy is. So the free energy is then, free energy F is simply given by minus 1 over beta, which is this periodicity of my Euclidean time, and then logarithm of Z. And then you can also calculate the entropy. So once you know what the free energy is, you can calculate anything you want about thermodynamics. And so in particular, the entropy is minus dF over dt. Okay, so this should be familiar to everybody who has done any statistical physics, right? So if I have the partition function, if I calculate it, whatever the partition function, this is my free energy, and then from free energy I can calculate anything, and in particular I can calculate the entropy. So these are the two assumptions which I'll be using here. Of course, the statement is that this is all nice and valid for normal fields. So now we are pushing this for gravity. Okay, and so that's what what Penrose was very unhappy with. All right. So how much time you have? That's perfect. So now we could do it directly for Schwarzschild and calculate what is the corresponding temperature and calculate what is the corresponding entropy from this thing here. But let me do it because we demonstrated everything on Rindler space first. And that's much simpler. So let's do it for Rindler first again. Okay. So remember, Rindler space is just a space of an accelerated observer. Are there any questions so far? No questions? All right, so let's do it. For Rindler first, and then we can, if we have time, we can do it for Schwarzschild as well. So we know that the Rindler metric, again, I write it down, is ds square is minus 1 plus ax square dt square plus dx square plus dy square plus dz square, if I put the other two directions as well. So that's my Rindler space, just a transformation of the Minkowski space. Okay, so to calculate what is the corresponding temperature in this space, the statement is you have to bicrotate your time. So I will just bicrotate the time. So the time here is the capital T. So I will bicrotate capital T to my new Euclidean time tau. Okay, so the first step is to bicrotate, rotate, and then we define tau to be I t. So now my Euclidean metric, Euclidean square, well, just dt square now becomes minus d tau square. And so this will be just 1 plus a x square d tau square plus dx square plus the other terms. So far, so good. So we just bicrotated the time. Yeah?
We just bicrotated the time?
Yes.
Yeah, but, well, I know it's just a trick, but...
It's a trick, yeah.
Yeah, but you, the local structure of... The local causal structure is associated with having this minus.
Yeah, you're completely changing time. You're completely changing everything, right? So once you bicrotate time, your space-time will look completely differently. It's a Euclidean manifold now,
Yeah.
and it has very, very different properties, different topology. Everything is different. I agree. Yeah. But that's the prescription, right? So for any normal field, you would just say, I look at what Euclidean time is doing. I introduce this tau, and then plug it for my Green's function, which I calculate. And then if I see that this Green function is periodic, then it's a thermal Green function. It's in thermal state. So now I'm doing this to the metric, right? I'm doing this to the gravitational field. So first, prescription here is really to bicrotate T, and yeah, this will be completely different than that. I agree with that. Yeah. All right, so that's the first step. So then the next step is to simplify this a little bit. So let's introduce a new coordinate rho, which will be 1 plus ax over a, so that d rho is dx. And that simplifies my metric a little bit. So if you look at this thing here, this is just a square rho square. So dse d square se is just rho square a square d tau square plus d rho square plus the other two. All right. So this looks simpler. And now I make it even more simpler. I just call this thing to be the phi square. So I'm doing a transformation that phi is a times tau. Okay, so if you do that, then this becomes just d rho square plus rho square d phi square plus the other two terms. So by the way, notice that on the horizon, on the Rindler horizon, which is located at x equal to minus 1 over a, rho is 0. So horizon, where the horizon was, so horizon, the original one, corresponds to rho equal to 0. But we know that the Lorentzian metric, the Rindler horizon is not singular. So the horizon was just a coordinate singularity. The spacetime was not singular there at all, right? So now the argument is, if the original spacetime is not singular on the horizon, the Euclidean rotatant one cannot be singular as well on the horizon. But the horizon here is simply rho equal to 0. So this thing here cannot be singular at rho equal to 0. So we demand that at rho equal to 0, there is no singularity. No singularity. So how to achieve that at rho equal to 0, there is no singularity? So if you look at this thing here, it should remind you something. What does it remind you? Huh?
Cylinder.
Huh?
Cylinder. Zeta metric.
It reminds you polar coordinates, right? It reminds you polar coordinates. If I go from Cartesian to polar coordinates, and this is my polar radius rho, and this is my corresponding angle phi, and this is just d rho square plus d phi square. So these are just polar coordinates. Okay, so polar coordinates. But of course, the problem is that polar coordinates are, well, of course, they are non-singular if I have flat space. But they may be singular. I can have a conical singularity in the origin. If my origin is here, and then this is my rho, and this is my phi, I could have, in principle, here a conical singularity. And to avoid the conical singularity, to avoid this thing, I have to make sure that the angle here goes from 0 to 2 pi. It's like with the string yesterday. So remember, yesterday we had almost a flat space, right? We had precisely this type of the metric, but the problem is that the string actually cut out of the spacetime some conical deficit, and so then there was a conical singularity. So now I cannot have that because conical singularity is singularity, and I forbid any singularity here. Okay, so polar coordinates to avoid conical singularity. We have to make sure that the angle phi is really identified with the proper period 2 pi. Okay, so this is then, if this is true, then this is just polar coordinates of flat space, and then there is no singularity. All right, so we have that. But what it means is that, remember, phi is just a times tau. Okay, so if I identify phi with period 2 pi, that means that I have to identify tau. So from here, follows that tau has to be identified with tau plus 2 pi over a. Okay, I'm just dividing. So tau is phi over a, so it's 2 pi over a. In other words, my time, my Euclidean time, has to be periodic with this period beta. In other words, we just derived that this spacetime, the Rindler spacetime, is actually thermal spacetime with the temperature 1 over beta, which is equal to 1 over a over 2 pi. this is the Bill Unruh temperature. This is the Unruh temperature. Unruh. Which tells you that the accelerated observer will actually see Minkowski space as filled with blackbody radiation with the temperature proportional to the acceleration of the observer. Okay, so see this like maybe 3 lines of derivation here, and you derive Unruh temperature, Unruh radiation. So what it means is that if you actually start running really, really fast and you accelerate a lot, you can cook a chicken by this. Right? So you hold a chicken and you start accelerating, and then you can cook it. Okay, so that's what it means. Are there any questions to this? Yes.
Is this calculation quantum mechanical since we made the WKB approximation? Or, like it seems like that coefficient function doesn't really.
So just a second. So here I wasn't doing the right-hand side. I was just doing the left-hand side. So this is like really using the quantum field theory. So this is fine in that respect. Of course, what may not be so fine is that this applies to standard fields, and it may not apply directly to gravity as well. So here we are just applying this to a metric, yeah. Other questions? Well, see that beauty. So we just derived one of the most important results in in physics. So then let's use the second part. So let's use the partition function part. So to that purpose, we have to calculate what is the Euclidean action for our metric. Okay. So in the WKB approximation, we just have to evaluate our action, which is the Euclidean action, on our classical solution, and the classical solution is that of the Windler space. Okay, so now let's calculate the action for our classical solution, which is the Windler space or Windler metric. And that's the Euclidean thing. So again, I'll be using this Euclidean big-rotated Windler metric here. All right. And that's the origin of minus sign. Perfect. Okay. So what is the action for gravity? Anybody tells me?
The determinant symmetry.
And
the Ricci scalar.
Perfect. So we have the Einstein-Hilbert action, which is 1 over 16 pi g whatever square root of g r d4 of x. So that's what you have seen, and everybody should know for the interview. Okay, so that's the Einstein-Hilbert action. However, we know that this action is ill-posed. This action has these boundary terms which contain the derivative of the metric. And these are ill-posed. So it makes the variational principle screwed up. So then I told you, well, we can kill these terms by hand, the first derivative terms on the boundary by hand. And that's done in terms of the other action, which is the Gibbon-Hawking term. And you will derive it in gravitational physics course. And it's just 1 over 8 pi plus 1 over 8 pi g. And then square root of h k d3x. So this is the boundary term. So this is an integral over space-time manifold. This is an integral over its boundary. And this is the Gibbons-Hawking term. Gibbons-Hawking. And this is just the determinant of the 3 metric on the boundary. And this is called extrinsic curvature. Extrinsic curvature. And you can easily calculate what this extrinsic curvature is that if you have the normal of the boundary, this is the normal of boundary, And then the extrinsic curvature is simply given by the covariant divergence of this normal. Okay, so this is the extrinsic curvature, and the latter formula you already know from your tutorial. All right, so basically all you have to do is that you say, well, I impose a boundary on my space-time here, and then I find the normal of this boundary, and then I calculate extrinsic curvature from this normal as this thing here. All right, so how do you do this? Is that our window space is valid for x bigger than x plus all the way to infinity. Okay, and then t goes to, so t is now the Euclidean t, so that's periodically identified with the period beta. So that's this thing here. And then I have also these other coordinates y and z. And so they in principle go to infinity, but I can consider only, let's say, the length of 1. So then the integral over dy and dz will give me some area in that direction. All right, so now we have to evaluate this thing here for our metric. Okay, so what is the first term? What does the first term give me?
It's 0.
It's exactly 0, because this is just a flat metric, right? So the Riemann has to be 0, so the Ricci is 0, so this thing doesn't contribute anything. So the only value of the action is actually contained in this boundary term. Okay, and so really the only thing you have to calculate is this k, and you have to calculate what is h and so on. So k is very simple. So n mu. So what we do is that we introduce the boundary. Let's say we place the boundary. We say will be at x equal to x0. Then the corresponding normal is just perpendicular to that boundary. So it will have 1, 0, 0, 0 component. I can calculate this k, and the k turns out to be just a. K turns out to be just a over 1 plus a x0. And finally, you calculate the determinant of the metric. So I'm plugging x equal to x0. So this term is not here, but the determinant is just given by this thing here. So it's 1 plus ax. So square root of h is just 1 plus a x0. All right, and so you just plug it here, and you calculate it. And so what you get is that your S and I may have a wrong sign here, but that doesn't matter. So maybe it's actually minus 1 over 8 pi g. I'll have to check that. So the action is equal to 0 from the Einstein-Hilbert term and plus 1 over 8 pi g. And then square root of h is just 1 plus a x0, 1 plus a x0, which is square root of h. And then k is just a over 1 plus a x0, a over 1 plus a x0, and then I have an integral over d tau, dy, and dz. What is integral over d tau? It's periodic. It's period beta, so it's beta. So this is beta times integral dy and dz, and I just say this is sort of compact, and then gives me some area in this perpendicular direction. All right, so now you find that, of course, this cancels that, and you have a. So it's a beta divided by 8 pi g times the area. Okay, and then, so Probably there is a minus sign. Sorry for this. I think there must be a minus sign here because I needed minus sign. So there's a minus sign here. So let's put minus sign here. All right. So this is my S. So the next thing is I have to calculate the free energy. So free energy is minus 1 over beta logarithm of z, but as z is e to minus s. So it's s over beta. Oh no, let's put s Euclidean so that it's not the entropy. S over beta. Okay, so that's equal to, I just divide by beta, so it's minus a over 2 pi, let's set g equal to 1, a over 4. That's the free energy. And then finally, you notice that this is what we called the temperature. So this is minus T a over 4. Now you calculate the entropy, which is minus dF over dt. And that gives you a over 4. Which is basically what Bekenstein told you. But now we are getting this factor 1 over 4 due to Hawking as well. So you just confirmed by this calculation that also the entropy has to be a over 4 as Hawking actually calculated. So really it's this calculation here for Rindler. You can do the same calculation for Schwarzschild. You will do it in your tutorial today. Perfect. And you see that you can derive using just these two simple assumptions. You can derive black hole thermodynamics. Isn't this amazing, really? So by the way, notice that typically F, if you look at, it's a Legendre transformation of internal energy. So it's energy minus Ts. That's what you find in Wikipedia. Free energy is internal energy minus Ts. So now internal energy is, of course, the total energy of the space-time, which is m, which is 0 here because we don't have any mass. So this guy is gone, and it's minus Ts. And this is what we are finding here. So that's another way how you can find the entropy is a over 4.
But in this Rindler space, if you're not moving, then you will see like an entropy 0, a 0 entropy. So
what do you mean if you are not moving? So if you are an inertial observer in Minkowski space, you will see 0 entropy and 0 temperature.
yeah.
If you are accelerating, then you see this temperature and that entropy associated with the horizon. So you have this Rindler horizon which has some area A, and then you just prescribe to it certain entropy.
But that's contra-intuitive with thermodynamics, right?
Because?
Because the entropy would depend on how you move.
Well, it's pushing thermodynamics for regimes where it was not. Yeah. All right. So as I said, so you can do the same thing for the Schwarzschild now here. And so for Schwarzschild, you will also find that the temperature, so now you can see all the bloody details in the notes, but you will also do them in your tutorial, so don't worry. So now if you return back to Schwarzschild, so back to Schwarzschild, you can follow all the steps. So you bicrotate T to I tau, and then you play with the metric to bring it into this form, d rho square plus rho square d phi square. And then you'll see that to avoid the conical singularity, I have to identify phi with 2 pi, and I have to identify the imaginary time with something else. And so you'll find that the temperature for Schwarzschild is 1 over 8 pi m, which is the surface gravity divided by 2 pi. Okay. So by the way, notice that the surface gravity in Schwarzschild is precisely our Rindel acceleration A. Right? So that's you can switch one for another. And then if you did repeat now the action calculation is now slightly more complicated because it has to be renormalized. So you get infinity if you calculate the action just using these two terms. And to kill, even for flat space, actually. So to actually get a finite result, you better require that the action for flat space is 0. And that forces you to actually subtract some counter term here. Okay, so if you subtract that counter term here, so that the flat space has zero value of the action, and then now use it for Schwarzschild spacetime, then you will get again that the entropy is A/4. So entropy is A/4 from that calculation as well. All right, so the black holes indeed have temperature. So black holes have temperature and entropy. So the last thing which I want to, yeah?
Is there any interpretation of this entropy as like a log of number of microstates?
Haha, very good. Yes and no. So people reproduce this formula as over. So that's of course the quest for quantum gravity, right? So any consistent theory of quantum gravity should explain this A/4 by counting microstates. Of course, there's partial success in both theories, in loop quantum gravity and in string theory. So in string theory, in the late 90s, people actually could. So you can form the black holes out of some combinations of strings and branes and stuff like that. And then you can actually calculate in how many possibilities these things can form the same black hole, which looks, from outside the same. And yeah, and then they reproduce this formula. But the problem is that that wasn't for normal black hole, like Schwarzschild black hole, but it was for a 5-dimensional BPS supergravity black hole. Okay, so these black holes are nice to understand in string theory. String theory has real troubles understanding black holes like Schwarzschild black hole, and so nobody was able to reproduce for Schwarzschild black hole in string theory. Okay, so that's but for other black holes, for really nice supersymmetric black holes, yes, you can do it. So now in loop quantum gravity, there is also a counting argument, which, however, now I don't know, 3 years ago, people said it's completely wrong, and they came up with another argument, and then it's very clear that you can really do it. But at least that will be for Schwarzschild black. So yes, so people are trying to reproduce this by counting argument, by really counting a logarithm of number of states. You can form your black hole, but the success so far is only partial, I would say. Okay, so I have 10 minutes, so in 5 minutes, I want to tell you about something really exciting. If you go to any string theory seminar, you will hear the term Hawking phase transition. Okay, so I want to discuss what a Hawking phase transition is. So that if you come to any string theory seminar, you know what they are talking about. So Hawking phase transition. So you have the free energy, which I said is typically E minus Ts, which is the mass of the black hole. So free energy is the mass of the black hole minus temperature of the black hole minus entropy of the black hole. Okay, so this is, so if I calculate, my black hole is thermodynamic object, it has the temperature and it has the entropy, I can construct the corresponding free energy. Okay, so now you can plot this free energy, and you know that in equilibrium, the state corresponding to global minimum of the free energy, global minimum of free energy is the one which occurs. Free energy is preferred. Thermodynamically. Okay, so if you find the free energy, the states which correspond to the global minimum of this free energy are the ones which happen in equilibrium. So now Hawking page transition refers to something like Schwarzschild black hole, but now Schwarzschild in ADS. So you just take, not in vacuum, but with a cosmological constant, and this cosmological constant is negative. So consider Schwarzschild ADS black hole. So lambda is negative, but otherwise it looks like Schwarzschild. So lambda, which is negative. And then you can plot how this free energy looks like. Okay, and so what you find out, so the free energy is a function of temperature and lambda. So now I can plot this for fixed lambda. And so free energy as a function of temperature will look like this, and this is for lambda fixed. And how it will look like is it makes this thing here. Okay, so now the points on this diagram correspond to different masses of the black hole or different R pluses. So R plus is small here, and then every point on this diagram makes bigger R plus. So then you go this direction here, there is this cusp here, and then you go down, and so this is large R plus. In other words, this line is sort of large black holes, and this line is small black holes. Okay? Then you immediately see that if I want to globally minimize the free energy, then the branch of large black holes has lower free energy than the branch of, it goes all the way here, than the branch of small black holes, and so large black holes are thermodynamically preferred. However, that's not the whole story. You also have radiation. So you know that your black hole actually radiates, this Hawking radiation, so there's some radiation present in the space-time. And then you can calculate what the free energy of the radiation is. And the free energy of the radiation, so Hawking and Page estimated this, it's approximately 0. It's only a teeny tiny number of quanta. So this is the free energy of radiation. And now you should be basically thinking about the combined system of radiation plus black hole. Okay, so now you just compose, it's like a competition between radiation and a black hole. So now you see that all the way up to here, the radiation has lower free energy than both types of black holes. Well, this one here and that one here. So all the way up to this temperature here, which is called T Hawking Page, the radiation is winning, has lower free energy. But at this point, at this temperature here, you see that this thing has lower free energy than the radiation. Okay, so then this is winning. And so there will be a phase transition from radiation to a large black hole. So there's a phase transition from radiation to large black hole, which happens at T Hawking Page. You see that the free energy, the minimum of the free energy here is continuous, but the derivative is not. That's a characteristic of first order phase transition. So that's a first order phase transition, which happens at this T Hawking Page. Right? So you can think about it like I have radiation in my space-time, and I'll start heating it up. So I'm heating it up, and the radiation is happy. But until I reach this T Hawking Page, and the radiation is no longer happy and collapses to form a black hole. Okay, and so this is what's happening here. at this point.
What kind of radiation is it?
Huh?
Which kind of radiation is it?
Any radiation you can have in ADS space, so scale particles, whatever. So you can think Hawking radiation.
What do you mean by heating it? Heating it?
Aha, very good. So there must be. So you are doing thermodynamics. So you're pretending to do thermodynamics. So you pretend that you have some control parameter how you can actually control the system. So I have an infinite bath around my black hole which heats my radiation or something like that. So it's like all thought experiment. But okay, very good. So we have this radiation to large black hole phase transition, but due to the ADS-CFT correspondence, Witten came with the idea that basically it corresponds to confinement and confinement phase transitions in quark-gluon plasma. And that's why people are really excited about these type of phase transitions in ADS black holes, because now they describe some phase transitions in your coupled CFTs. And so this is really current research at this point. All right. So let me stop here. So in your tutorial, yeah.
What's the point along that?
On the cusp? It's simply an interesting point. So when you say, when I say R plus is small or R plus is large, what does it mean? It means with respect to the ADS radius. So lambda has some associated radius to it. So you can translate lambda to some fundamental scale in your ADS space. So small black hole will be such that R plus is smaller than this ADS radius, and large is bigger. And so this happens precisely when something like R plus is something like L, where lambda is 1 over L squared or something like that. So yeah, it tells you. But this is interesting point. It can show that, for example, the specific heat of black holes here diverges and stuff like that. So it's a cusp. It's an interesting point as well, but it's not that as interesting as this one here. All right. So let me just finish here. So I would like to thank you so much for attending this course. I hope I convinced you that GR is a beautiful theory, and that the Einstein equations are probably the most beautiful equations in physics whatsoever. So especially because of their double agent role, and because that you have geometry on the left-hand side and you have matter on the right-hand side, and they basically change the understanding about the space-time and understanding about everything. I also hope that I convince you that GR is a physical theory. It has passed so many experimental tests as basically no other theory, starting from the first perihelion shift of the Mercury, and then going through the light bending, and then the prediction of the black holes and subsequent observation of these black holes, and also seeing how much energy is lost due to gravitational radiation and to the direct observation of gravitational waves. So I went through Nobel Prizes, and I counted something like 8 Nobel Prizes awarded to something related to general relativity, where I cheat a little bit and I calculate. I count also, for example, the CMB discovery, which, however, is nevertheless related to the Big Bang. And Big Bang you can predict only in general relativity. So there are 8 Nobel Prizes related to general relativity. 2 of them very direct about the gravitational waves. But interestingly, Einstein never did get Nobel Prize for general relativity. So at the time he got Nobel Prize, he got for the photoelectric effect. So by the time everybody believed that special relativity is right, and nobody believed that the Einstein explanation about photoelectric effect is right. But nevertheless, he didn't get it for special relativity. He got it for photo effect. But I think he would deserve one later for general relativity as well. So I would say that the biggest moral of the story is that, and there will be lots of people trying to convince you otherwise here, is that they will tell you should be doing hard calculations and not think too much. But the truth is, I think it's actually very, very useful to sometimes think about elevators, as Einstein did when he developed general relativity. So thank you so much, and look forward to the tutorial in the afternoon.